This isn't. No, I can do 2 centimeters. We're fine.
It has centimeters.
Yeah.
Calm yourself. Calm yourself.
I'm a little worried. Okay.
So let's do it between
There.
the center of that black thing and
Center of that.
the inside of that.
Well, that doesn't make sense, but I'll do that for you. Okay. And then
Sass factory.
that. Okay. It's about 76 centimeters, so 0.76 meters. Okay, I'm retiring.
Thank you.
Yep.
Wow.
Can I keep this?
So early? Must be an
Oh, I can help you with
entrepreneur.
more. I can be your lab assistant if you want.
All right. Well, maybe you can.
Woohoo!
All right.
My qualifications? I am.
So, you see this jack? I'm going to plug it in here. And I'm going to take these wires. They're called banana wires. And I'm going to plug them into the device. And so the black thing I just plugged in will be connected to what is called a multimeter. Are you guys familiar at all with multimeters?
I've seen my dad have one of those before.
Okay, yeah. Or if you come next semester, we'll use these a lot. So these will tell us voltage, resistance, and current at different places in a circuit. What we're interested in is resistance. So I plug the black lead into the black port, and I plug the red lead into the red port that has a resistance symbol on it, also known as ohms. And then I turn the dial to resistance. It's open.
10.80.
It says 10.80, 10.80, or that's actually 1,000 ohms.
Wow.
So 1, 2, 3, so 10,800.
Wow, that's a lot.
Okay? So our resistance original is 10,800 ohms. Well, what is that in temperature?
Not a lot.
I have no idea. But it's probably roughly room temperature, right?
Yes.
That makes sense.
So actually, let me move this. 10,800 ohms. Yes? So let's see. Thanks. I'll get back. with you
Okay,
shortly.
okay, thanks.
Because I've got to go over some stuff. I know you guys, just hang in there. This is better than me blabbing on about physics. Oh, this is physics.
Yeah, I was about to be like, what?
Hang in. So this is where typically the lab falls apart for everybody.
Great.
Perfect. Sony.
You should make a letter to
Oh, happy people.
ask them to pay you.
Here's how this works. You'll notice this is the chart that allows us to translate between resistance and temperature. So right now our initial resistance is 10,800 ohms. So if I look at the chart, if I'm super lucky, I find 10,800 on here. Does anybody see that? No, I am
There's
unlucky.
10,900.
Yes, and then there's 10,450. So the original resistance is somewhere between those two values. Do you see that? Okay. So we have to use something called linear interpolation, where we not extrapolate beyond our range, but interpolate within a range of values to translate this resistance into a temperature. Okay? And the way this works for a thermistor is as resistance goes up, temperature will drop. So if I were to try to create a flat or straight line between 2 points and use that to estimate the temperature, that is my goal. Well, what is my upper temperature for these two numbers? 24. Okay, so that is this value, and the lower temp is 23. Okay, you guys follow? And then what is the resistance at 23? 9, 21, right? 10, 9, 21, and then what's the lower one? 10, 450. So the actual temperature, my starting temperature of my copper tube is somewhere between 23 and 24 degrees Celsius. I know that because I just read the resistance on my device. The question is, you can't just say, oh, it's about 23.5. No, we're going to actually figure out exactly what it is. Okay, how might I do that?
You take the difference and then divide it. Well, 1 divided by the difference.
Can I? Good. Yes. Can I create an expression that describes this straight line? Can I do that? Okay. Harkening back to not pre-K, kindergarten, when we found the slope between 2 points. Not midpoint, because you're assuming it's 23.5. Might not be. Is it closer to 10,921 or 10,450?
9, 20.
Yeah, so it's probably going to be over here somewhere.
Okay, then a modification. A quarter point formula.
Well, or a formula. How about a formula that says y equals mx plus b, something like that. Can we do that? So how do we do that? So slope. And I can take what? Y, delta y over what?
X2 minus X1.
Yeah. So it's got to be this guy, right? Because that matches the 24.
Yeah.
Somebody doing this for me? That's a very small number.
Negative 0.00212.
Okay? That's my slope, and that's degrees Celsius per ohm. Ohms are units of resistance. So I can tell you that in the actual lab you have to do this 6 times. Well, think about why. Why might we do that if I had 3 samples?
Because you need to do it once for the initial temperature and once for the final temperature for 3 different samples.
Correct. And furthermore, this is only good for the starting temperature. I need to do a completely different setup of this for the final temperature. I can't use the same equation that I'm about to find because actually in the big picture it looks like this. It's actually a nonlinear function, and what we're doing is we're finding a straight line between a small segment of that nonlinear function. That's what we're doing. Is this exciting or what?
Or what?
It's the or what part that we're talking about. Okay, so I have found the slope. That guy. How do I get the y-intercept?
You plug in the y for the y and the x for the x. And the
Yeah, so I can pick either one of these points, correct? And I can come up with the y-intercept. So, I don't know, I'll use 23. So 23 is equal to negative 0.00212 times, I gotta use that value, right? 10,921 plus b. You guys remember doing this in Algebra 1? I know you did it in Algebra 1. It might have been in kindergarten, it might have been a little bit later. But Algebra 1, right? Okay. So somebody find b for me. All these numbers are different, by the way. My numbers are different than these.
46.168.
So b equals 46 point what?
168.
168. Okay, so let's finish. Oh, I need to write this down. Oh, actually, I'll just make this thing go up. How's that sound? By the way, after we do this craziness, I'll talk about the final while the water's boiling. Okay? It takes forever for the water. All right, so now I have y equals negative 0.00212x plus 46.168. Is everybody tracking on what we just did?
Yes.
I took 2 points, I found the slope between the 2 points, and then I found a function that describes the straight line that goes through those 2 points with a y-intercept of 46. That's way up on my scale that I drew there, as you can see, right? Not to scale, not to scale. All right, so really though, this is what? T equals negative 0.00212 R resistance plus 46.168. Do you guys see that really I have temperature versus resistance? X, Y. Is anyone paying attention?
Yeah.
Maddie?
A little bit.
Yes.
Negatively sloped. Now, what is my starting R? So what is my initial temperature? Someone?
23.238 degrees.
23 point what?
238.
There. That's just how we would have to do this. Every time we find a temperature or resistance, we have to translate it into temperature. Okay. You can see why this lab is chaos for me. Right?
Just cut it.
All right, and oh, by the way, didn't our spidey sense tell us that given it was 10,800, it would be closer to 23
Yes.
than it would be to 24? And that is in fact the case, right? 23.24. See? Okay. So, L naught is 0.76 meters. T naught is 23.24 degrees Celsius. So I can get rid of all that. All right? So now what I'm going to do is I'm going to set the water to boiling. And once it gets going, what I'll do is I'll take this thing and I'll put it on the end of the sample. And I'll set the micrometer. Make sure. I might need someone with some eyes.
I think we're all blind in this class.
Yeah. So what'll happen is once this is boiling and I plug it in, it'll push steam down the pipe. So it's changing the temperature of the sample. And once I see that I'm getting a lot of steam, I'll turn this thing on. The bad part about this apparatus is the gauge goes to sleep. It won't stay on. And so you don't want it to go to sleep while your sample stretches. It's bad. So we'll wait for the water to boil. We'll get it super boily, put it on there, and then we'll turn this thing on. Once we see it stretch, it'll give us a sense of delta L. Okay, and then we can calculate that and we'll find that. Sound good? All right. So.